Hello, everybody. So we're going to have a little more fun with enthalpy. But this is where we're going to do a little bit of a sort of a focus shift. For one, we're actually shifting from the textbook into the Ebbing text. So you're going to want to have the packet from the Ebbing textbook that I gave you. And in fact, if you want to save some time, you could go ahead and flip in that packet to page 247. Because we will be looking at example 6.5 and exercise 6.6 as we get started here. So notice right off the bat, on the front screen here, we see one big word in red letters. Red? Wow. I have a red pen in my hand. Maybe that's why I said red. How about yellow? You can see one big gigantic word in yellow letters, and that is experimentally. I don't know if you've realized up to this point, but up to this point, we have not talked experimentally. We haven't talked about doing something in the lab. In fact, everything we've talked about has been theoretical. You've been given values for Q. Remember Q? That was a while back. Q is just heat, whereas delta H is enthalpy. But you were given those values. You either were just directly given the value or you looked it up in an appendix. But as it says here, this will not always be the case. So today, instead of giving you theoretical information, which is from the appendix and different things like that, you are going to see how to calculate the values based on what we've done in the lab. So we actually, at this point, will then have an ability to compare numbers. So we have a theoretical data or a theoretical data set that we can look up, but then we can actually do it in the lab and see if our numbers match. And by the way, if that sounds like a pretty darn good lab exercise, then you've definitely hit the nail on the head, because we will have a lab upcoming that is going to do exactly what I'm showing you in this presentation. So maybe make a note to self that it's this 6.6 PowerPoint presentation that can be of great help to you in a lab that we have coming up. So moving on. This is, as it says, must know info, and I just love that it rhymes. So something called specific heat capacity. It's generally a shortened usage here, and we just call it specific heat. But what specific heat is it is a constant value, basically. It's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. It's actually sort of a similar thing to like a calorie, and how we had talked about calories before. So amount of heat required to raise 1 gram of a substance by 1 degree Celsius. Specific heat will receive, unfortunately, different abbreviations. If you are in the Ebbing textbook, and if you are looking, the handouts I gave you, that is, and if you're looking at page 247, just look at example 6.5 and notice kind of right in the middle of the gray boxes there that you'll see an S in there. That S is meant to be specific heat. However, on the AP equation sheet, they use C, lowercase c, by the way, for specific heat. Why the difference in the abbreviation, I don't know. It is a complete mystery to me. But what I want you to know is that I will use C to try to make sure that I am keeping with AP. But when you look at it in the textbook, you just have to be aware and be understanding that you're going to see an S there. So my apologies for that. The units of specific heat, or C, are joules per gram degree Celsius. Joules, grams, and degrees Celsius. And in fact, this is going to be the equation that you're going to be using. Q equals Cm delta T. And if you take a look at things, you'll recognize where all of these pieces and parts of the units are coming from. So the gram is obviously coming from the M, which, as the yellow says there, is mass. The degree Celsius, well, that's coming from the delta T, which is the change in temperature. And then the joule is actually what your Q is measured in. So the C value, let me take that away for a second. So the C value is meant to appropriately cancel out the gram and the degree Celsius to leave you with joules, which is what your Q, your heat, is measured in. So hopefully that makes some sense. And if it doesn't, it will once we continue on here. So values for specific heat, as it says here, depend on temperature. And if you take a look at table 6.1, I guess my apology there, I had you flip to a kind of a different page. Let's find 6.1. Actually, it's on the facing page. It's on 246. And you can see a little table down there at the bottom, and you'll recognize that it says aluminum and copper and ethanol and iron and water, and it gives you a specific heat. You can see the joule per gram degree Celsius. But I specifically want you to notice at the very bottom, there's a little asterisk, and it says values are for 25 degrees Celsius. Well, that should make sense. That's standard state condition in thermodynamics. But if I change the temperature, the specific heat will change. And so it is important that you run these reactions at a typical 25 degrees Celsius, at least, within a little bit of difference. The other thing you might notice in table 6.1 is that there is something right next to it called molar heat capacity. Molar heat capacity, go back up to the definition, which is way up here. If I'm going to define molar heat capacity for you, amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So molar heat capacity, just notice the difference in the units. It's joules per mole degree Celsius. So you may deal with that at some point, but it's usually going to be pretty clear what you're working with. But you would need to use a molar heat capacity. And FYI, the AP equation sheet uses a capital C instead of a lowercase c to mean that molar heat capacity instead of specific heat capacity. I feel like it's just a big jumbled mess, but generally speaking, you will use specific heat capacity way more than molar heat capacity. You just want to know that the one exists is pretty much my only issue. So if you would take a look then at page 247, which I drew you to in the beginning, I'm just asking that you take a look at that example. It says relating heat and specific heat, and just look at the solution. Read the question, of course, look at the solution, and recognize that all it is plugging and chugging. So they ask you, calculate the heat absorbed by 15 grams of water. The temperature raises from 20 to 50. And the specific heat of water is 4.18 joules per gram degree Celsius. So just take a look at that and notice what they do, okay? Simple plug and chug. Pause the video, please. Okay, so if you have any questions about that example, definitely let me know. But if you do have some questions, I think I can probably figure them all out for you as we continue on and do exercise 6.6. So given that you have an example right above in the example, that is, please try the exercise. So please pause the video and try it, and then I'll show you the answer in 1 second. Okay, so the answer should utilize the following values. You can see your specific heat, your mass, and your temperature change. So when you factor it into your Q equals Cm delta T, it would all come out kind of looking like this. You can see all the various parentheses and such. And your final answer should be 1.80 to proper sig figs times 10 to the second joules. Okay? So hopefully we're okay on that one. And the next thing that we're going to do then is actually get into enthalpy, because you may have noticed that we just determined heat, but we didn't actually go on to kind of the next big thing. So enthalpy comes after Q. So finding heat of reaction experimentally. This is where we're really going to get into what the lab that we will come to is going to do. So first, if we're going to do this in a lab, we're going to need a special piece of laboratory equipment. It is super, super, super duper technical, okay? It's called a calorimeter, meaning that you can actually get calories and things like that. But it's going to allow us to determine temperature changes. And like I said, it's incredibly scientific. It's very technical. It's like the most awesomest piece of laboratory equipment you'll ever work with. It is, by definition, a device used to measure amount of heat absorbed or evolved during chemical reaction. So again, you can see the delta H value kind of within those words, amount of heat absorbed or evolved. And a calorimeter, ladies and gentlemen, the one we're going to use, it's called a coffee cup calorimeter. Oh, wait, so you're seeing the irony in all this? Okay, yeah, me too. It's actually 2 styrofoam cups nested inside of each other with a piece of cardboard with the thermometer stuck through it. And the cardboard, by the way, is the lid, and you just jam a thermometer through it. Can you picture it? Yeah, technical. Very, very, very scientific. Ask me. I'll show you tomorrow exactly what it looks like. You're going to be blown away. Yeah, and you may be, kind of thinking, really? Styrofoam cups? This is AP Chemistry, Mrs. Seagrave. So honest with you right now. The styrofoam cups really work awesome. I mean, styrofoam is an insulator, and when you put two styrofoam cups together, you get a little bit of air pocket between those two, and air is an amazing insulator. In fact, that's why down coats, the big, big, heavy, puffy winter coats, the down coats, that's why they're made of down, and that's why there's so much in there, because it's not the down. It's the fact that down can trap air, and air is a great insulator. So that's what styrofoam does. The styrofoam itself is insulating because the styrofoam has so many air pockets, and then you produce another little pocket of air between the two cups. So no joke, it is actually a really, really well-designed piece of laboratory equipment. It just doesn't seem all that fancy. I do have a fancier version, so ask me about that tomorrow. I will show you my slightly fancier version. But this is what we will use in the lab. And what we're going to do to find heat of reaction is we are going to take those styrofoam cups. We're going to put a known mass of chemical in there. And it has, of course, a set C value or specific heat. And then as we add some water or maybe another chemical like an acid, we can monitor the change in temperature. So it would be at room temperature as we started. And then as the reaction proceeds, we would notice either a rise in temperature or a fall in the temperature. And we can monitor that through the thermometer that's jammed through the cardboard lid. I mean, wow. It really doesn't get much simpler than that. Once you calculate Q, which by the way is the examples that we just completed, we found a Q value. Once we find Q, then we're going to be able to find a delta H value. So it is a successive set of equations that we're going to have to do in the lab to be able to work this out. So again, so we've got two different options for you here. We have the coffee cup one. I've got the fancier version I'll show you tomorrow. But the real fancy version is called, yeah, example to come shortly. I'll do that in a bit. The big fancy version is actually called a bomb calorimeter. Yeah, not that kind of bomb. Don't get excited. A bomb calorimeter, actually, if you are still in your Ebbing handouts, flip to page 249 and look at the figure there at the top of the page, and you will see a little cartoony drawing of what it looks like. And the thing to notice about this is that this system is completely closed. Unlike the coffee cup variety, is it possible for heat to escape? Yeah, definitely. And in a bomb calorimeter, there's no chance for any heat to escape because it's all completely sealed. And so you can get a very, very accurate amount of temperature change, and you're not going to lose any to the environment. It is way more accurate, of course, but what we will do is totally fine. You can probably imagine why this would be especially good for gases, again, being a closed system and the gases can't escape. So I just want you to at least have heard of it, because you may, depending on what you do in college, you may actually see it in college. So there you go. I've never seen one. Wasn't that good, I guess. I don't know. Anyway, moving on. Okay, so this is where we're going to get to our final kind of showdown here with this Q and delta H and what we're going to do in the lab. So on page 250, I want you to take a look at exercise 6.7, and this is where really the rubber is going to meet the road. What we're going to need to do here is really break this all down. So do me a favor. Pause the video, read the problem, okay? Pause. Okay, so after you've read that, you may come away from it a little bit confused. There's a lot of numbers. There's an equation. They're saying, for simplicity, assume that the heat capacity and the density of the final solution in the cup are those of water. I mean, some of the verbiage that they use is sometimes tricky to get through. But I promise what they're telling you in there is actually not that bad. So let me break the problem down for you. First off, would you agree that this is the equation? Well, yeah, I just lifted it directly from the textbook, so no big deal. If you look carefully, you'll see that it gives you information as such. It says you've got 33 milliliters of hydrochloric acid. It says you've got 42 milliliters of sodium hydroxide. And it also tells you the molarity of the hydrochloric acid, a 1.20 molar solution. They do give you the temperature change, and then they're asking you to find the delta H. Now, please note, everything that you see right here Isn't this something we could do in the lab, right? We could have a known molarity of a chemical, and we could knowingly put 33 milliliters of that chemical into a coffee cup calorimeter, and then we could knowingly add 42 milliliters of a sodium hydroxide solution. So this is all very easy. And then we have remember, thermometer stuffed in through the cardboard lid, and we got a 25.0 degrees Celsius reading on our thermometer before we started, and then we added the sodium hydroxide, and the temperature shoots up to 31.8. Okay, so all very reasonable bits of information that we would have, and they're asking us to find delta H from that. So it mentions, again, in what I read just a second ago, assume that the heat capacity is of water. Wait, why can I do that? Because I added acid and base. I didn't add water. Oh, but we pretty much did. Do you notice that the molarity of the acid is given as 1.2 molar? That's a relatively low molarity. Just FYI, it's a pretty darn low molarity. And so we can make an assumption that these are aqueous solutions, which actually it tells us there, right? Aqueous. If this was highly concentrated, it wouldn't say aqueous, it would say liquid. And the same thing with the NaOH. So the fact that it says aqueous means that the majority of what we're doing is just in water, meaning that it's totally fine to use the specific heat of water, okay? So we are going to be able to use water, and you will use the exact same idea in the lab that we will be doing. You will be using hydrochloric acid, you will be using sodium hydroxide, and you will be assuming that your specific heat, which by the way, this should be a lowercase c, my apologies, but you're going to assume that you're going to use the 4.18 for the specific heat. It also then tells you to continue that same sentence that we were working with. It says, assume that the heat capacity and the density of the final solution, I'm sorry, I'll get to the density in a second. I'm sorry, wrong sentence. The very last sentence. Also assume that the total volume of solution equals the sum of the volumes, meaning that when I end this thing, I'm probably going to be working with, I don't know, like 75 milliliters, because 33 and 42. Okay, so that's what that means. So that right there, I know it's a lot of talking, but that's just breaking down the one question and figuring out what info we have and what values we're working with, okay? So what equation will we have to use? The equation we're using, and I mean mathematical equation, not chemical equation. So Q equals Cm delta T. And we know what C is. We just talked about that. We're going to use the specific heat of liquid water. And we have the delta T, right? But we need a mass. We had volume. But wait. We have something else. And this is the other thing that it mentioned. The density of the final solution is that of water. Use the density of water to convert milliliters to grams. And again, this is possible because we're assuming that we are working with a very lowly concentrated solution, and we are assuming that we have really just mostly water. So we know that we have 75 milliliters, and that would be our total because we did add two different volumes again. And then the density of water is 1 gram per milliliter. So this is really hard math, I know, but that leaves us with 75 grams. So now we have our mass, and that was, again, if you know the tricks, it's pretty simple. So we plug it all in, and we do our math, and we get 2134 joules, and that would be our heat. Well, we have to round that, right? Because we actually had here the 6.8. So for sig figs, we need to round that. However, at this point, it's still appropriate to stick with the 2134 because we do have another calculation to go. But if this would happen to be our final answer, we would need to make sure we round it for sig figs. So FYI. But we're not done yet because they asked us for H, not Q. And this is Q. So how in the heck do we get to H? I'm glad you asked. All right. So first off, before we even think H, did you notice that the temperature rose during the reaction? It got hotter. It released energy. Is that endo or exothermic? Yeah, that's exothermic. So what's the sign of Q really supposed to be? If it's exothermic, that's a negative, yeah? So really, your answer at this point should be negative 2100 joules to proper sig figs, or the delta H is also the negative 21 joules per mole for this reaction. I'll explain that in a second. And this is where I tend to get people that get really upset with me, especially math people, because we calculated this and we didn't get negative. We got positive. Yeah, I realize that. But this negative, and this is where you're going to make, just really listen, just go with me here, promise. This negative is not a mathematical negative, it's a descriptive negative. What that negative is telling me is that the equation was run and that it was exothermic. So it's a descriptive thing. It's like having an adjective in front of the number. I realize that mathematically it is significant to put a negative in some place where you don't think it belongs, but I promise you that this is the way that it's done. And it is, again, like an adjective to describe the word afterwards. And in this case, it's describing the 2100 as exothermic. So this value that we've calculated, the negative 2100 and the delta H also, it's specific to the experiment, not the actual chemical equation. Because remember, the actual chemical equation deals with a mole being used up of each one of these, and we didn't actually use a mole. So remember, Q, delta H, all these heat things, they're extensive properties. It means it depends on how much you have. So I have to understand that when I did this reaction, I didn't use a full mole of these chemicals. I used a lesser amount. And that's why I have here per mole of this reaction, because they actually want a standard value. They want give enthalpy change for the reaction, and they want it based on the chemical reaction, not the experimental reaction. And that's maybe the next thing that's a little bit tricky to decipher in terms of the wording. So because the reaction specifies 1 mole of HCl and 1 mole of NaOH, you got to ask yourself, did I use that amount? And the answer is obviously no. So how much did I use? How many moles did we actually use of these two chemicals? Did you notice it actually said that we have an excess of sodium hydroxide, which means, that's code, remember, for I don't care about it. But the HCl, we were given a molarity and a volume, and it didn't say anything about excess, so that's our limiting reagent, so that's the one that actually matters. So what we're going to want to do is some typical things that we've done in the past. If you're given a volume and a molarity, dude, use them. Get the liters canceled out and get your mole amount. And so that's what I do here. So I now know that I did not start with 1 mole of HCl. In fact, I started with 0.040 moles. That's a pretty significant difference. So now this delta H, notice here I went back to the 2134, took the sig fig stuff away so that I had a more accurate value. So my delta H is actually negative 2134 joules every time I react 0.04 moles. Well, I want it for 1 mole. So what I need to do is do that math. Simply do the division. Negative 2134 divided by 0.040 gives me negative 53,350 joules per mole. If I want to create a more workable value, instead of using a number in the tens of thousands, I can simply divide by 100, divide by 1,000, and then convert that into kilojoules to have a 2 significant figure final answer of negative 53 kilojoules per mole reaction of the reaction listed in the book, 1 mole of HCl and 1 mole of sodium hydroxide. So that would be my final answer for those values. So again, you're going to be doing this in the lab. You will have all the values that we'll collect, temperatures and such, and then you'll get this answer, for instance, this one here at the bottom in yellow, and then we'll be able to also look up theoretical amounts based on our standard enthalpy of formation information that we did yesterday, and we'll be able to compare those values together. So this presentation is very much about your lab. The previous presentation that we did was very, very theoretical, but we can tie it to the lab. So understand that these two presentations will go together for your lab. Okay, have I made that abundantly clear? Cool. Oh, we're done. Sweet. All right, so we'll see you tomorrow. We'll talk it over, and we'll get you all squared away. Bye-bye.